So we have so much mass because of the portability. That's why like the operating system also needs a portability. Anyway, so today I'm going to talk about AutoV and Automotive Testbed for real-time virtualization. So as we know, the several physical systems, like the automotive systems, are becoming more and more complex. We have hundreds of tasks running on dozens of ECUs. And these tasks require high performance and strong isolation, which means these tasks should not interfere with each other, no matter what they are doing. So we have been discussing how to eliminate the interference entirely. We argue that the multi-core virtualization could help handle such complexity because we can consolidate the legacy systems into virtual machines on multi-core processor. And because the multi-core processor could be more powerful, each legacy systems can have better performance and smaller size, weight, and power consumption. So this is nice, but this virtualization technology also introduced new challenges for the timing isolation. One of the challenges is the interference coming from the tasks. If we look at the multi-core virtualization systems here, we have multiple tasks running in multiple virtual machines. These tasks may interfere each other in terms of the timing. This interference may come from the same VM or the different VMs. If we look into the shared multi-core platform, we find that this interference comes from the shared components on the multi-core platform, like the CPU resource, private cache resource, share resource, memory bank, memory bus, and I/O devices. So we propose the Artisan with Washington University, our collaborator, which aims to achieve the timing isolation. So we look at the CPU resource, private cache resource, and shared resource, and we provide the mechanisms to eliminate the interference come from the CPU resource and shared resource. We provide the analysis techniques to analyze the interference from the private cache resource. So this is the real-time virtualization. We ask the question, when we want to use the real-time virtualization to automotive system, we ask the question, does real-time virtualization really provide the timing isolation needed specifically for the automotive systems? In all of the papers we publish, we use the benchmarks of synthetic workloads. But there's a gap between the benchmark we use to evaluate the work in the paper and the real applications. So we ask this question, and then the problem becomes how to evaluate the system. The current status is that our real-time community has a real-time virtualization such as the Artisan, but most of us don't have the privilege to access the real automotive platforms or the real automotive applications. So if we want to evaluate the real-time virtualization, we need these real applications. So that's why we propose the AutoV to reduce the gap between the real-time community and the automotive companies or the automotive applications. So AutoV is just the automotive testbed for the real-time virtualization, aims to help evaluate the timing isolations provided by the real-time virtualization for automotive systems. It consists of two parts. One is the automotive racing car, which provides the automotive applications as the evaluation workload. And the other is the Artisan, which provides a state-of-the-art timing isolation mechanism for multi-core virtualization systems. So in the rest of the talk, I will first talk about the automotive racing car developed by our lab, and also the Artisan, before I talk about how to integrate these two systems to get the AutoV. Once we get the AutoV, I will show some evaluations. Now let's first have a look at the autonomous racing car. So the autonomous racing car was developed in our center, and when we joined the competition last October in Pittsburgh. So what this car does. So this car can drive autonomously in an indoor hallway. Give me a map. So this is like the map. And all of this are handled by the car itself. It has three modes. In the first mode, the car will drive straight in the hallway, and using a PD controller. And when it's getting close to the corner, it needs to slow down. So it gets into the brake mode. We use the idea of the anti-blocking systems used in the current commercial cars. Basically, we don't do a hard brake, we brake and release the tires so that to prevent the car from sliding. And once the car speed is slowed down, we will get the car will get into the turn mode. It will start to detect the corner to localize where it is and apply a constant steering angle to make the turn. Once it gets out of the turn, it will get into the fast mode and repeat until it gets to the finishing line. So this is the high level idea of the functionality of the car. Now let's have a look at the video which took in the computation showing how the car runs. So in this video, the car runs in average speed of 8 miles per hour, and the top speed is about like 16 miles per hour. Yeah. In the left corner is the map. So this picture is a team for this racing car. So we have 4 PhD students from our group and 1 visiting student, the girl from Korea. So this is the autonomous racing car. Let's look at the architecture of the car. So this car is built from a remote control car. On top of this car, it has an embedded board. The organizer asked us to use the NVIDIA Jetson board, but we are not limited to this board. And we also have a LiDAR to do the perception to detect the walls and also to detect the distance to the walls from the car. On the embedded board, we run the Linux and the ROS as the middleware. So ROS is short for Robotic Operating Systems, which is widely used in the robotic community. It is a PubSub communication middleware. And it also provided a lot of packages to help us control the actuators. We build the application based on the ROS. Each of the node is a ROS node. Basically, it's just a Linux process scheduled by the underlying Linux. And these nodes are communicating through the PubSub network. And there are actually only 3 main functionalities. The LiDAR gets the information, and the controller will take the information and compute the position of the car, like the height of the car, and the height. Most importantly is the height of the car and the distance the car to the wall, and then send the signal to the actuator. So this is the architecture of the car. We have seen the autonomous racing car briefly. Now let's have a look at the second part, the Artisan. So the Artisan aims to provide the real-time capabilities for multi-core virtualization systems. Right now, it has 2 mechanisms. The real-time CPU scheduling tries to eliminate the interference caused by the CPU resources. And also, it provides the dynamic shared cache management, to which basically provides a strong isolation for the tasks running in the VMs. Here I make it like dynamic. Basically, it can also support the static cache management and the dynamic management, and it is based on the Intel cache allocation technology, which is similar to the cache-way-based cache partitioning. And due to time constraints, we only look at the real-time CPU scheduling here. Okay, before we look at the real-time CPU scheduling, let's look at how Zen handles the CPU scheduling problem. So this is the environment. It has multiple VMs. Each VMs run on multiple vCPUs. The vCPUs are scheduled on multiple physical CPUs. By default, they use the credit scheduler, which is a round-robin scheduler with proportional share. it doesn't provide any real-time guarantees for the vCPUs. What does this mean? This means that when you configure a system, so the amount of CPU results a vCPU gets depends on who's running in the systems and what's their configuration. The more vCPUs are running in the systems, the less CPU results you get. So that's what the credit scheduler does, and it doesn't provide the real-time guarantees. In order to provide the real-time CPU results guarantees, we develop a set of real-time schedulers. We investigate the earliest deadline scheduling, first scheduling policy, and also the real-time, the rate monotonic scheduling algorithms. We also compare the global scheduling versus the partition scheduling. So based on the evaluation in our paper, we observe the global EDF scheduling performs best in the empirical evaluation. So we upstream the global EDF scheduler in Zen, which is the popular open source hypervisor used in the current cloud computing. It also, actually, the Zen community is also looking for the automotive applications. I know some companies are making money from this. So this global EDF scheduler has been incorporated in as the RTDS scheduler since 2015, and we are currently maintaining scheduler for the community. So we also we wrote the scheduler for Zen 4.7 last year to make it more efficient. So basically, the first version of this scheduler used the time-driven scheduling. The scheduler was triggered every 1 millisecond. Sometimes it's not necessary to trigger the scheduler. So we changed it to the event-driven scheduler so that the scheduler can be more efficient. So this is the high-level idea of the RTDS scheduler. Now let's look at how it works. So in the RTDS scheduler, each vCPU is specified as like a periodic task. It has a period and a budget. In this example, this vCPU has period 10 and budget 4, which means this vCPU will get its budget at the beginning of every period, and the vCPU's budget will decrease when tasks run on it. If there's no task running on this vCPU, its budget will be kept the same. When we have multiple vCPUs or multi-core processor, the scheduler will schedule the vCPUs based on its priority. The vCPU with earlier deadline will have higher priority. And all of the vCPUs with budget will be kept in a run queue, which is sorted based on the priority. Whenever the scheduler is triggered, it will start to pick the vCPUs from the top of the run queue and put it to the physical cores, so that we make sure that at any time the vCPUs that's currently running have the highest priority. For those vCPUs that has run out of its budget for the current period, it will be put into a depleted queue sorted by the next release time. So the scheduler won't handle this one until the vCPU's budget got replenished for the next period. When that happens, the vCPU will be moved from the depleted queue to the run queue and get involved in the scheduling process. So this is the RTDS scheduler. Okay, now we have covered the autonomous racing car and the RTZ. Let's combine them together to get AutoV. So we still have the same hardware. We still have the same remote control car and the same embodied board. And on top of the board, we don't run Linux anymore. We directly run the RTZ or Zen. And on top of the Zen, we run several virtual machines. In the virtual machine, we run the Linux and the ROS. So we put the racing application we developed into one VM and all of the raw service and the drivers in VM 0, and put all of the non-real-time tasks into another VMs. So this is the high-level idea of the architecture when we want to integrate the racing application to a virtualization environment. But it's not as straightforward as I described here, because there are two things to handle. First is that Zen or RTZ cannot run on this NVIDIA Jetson board. This is because the board vendor has some special design for their general interrupt controller, which cannot be handled by Zen, so we need to pass it. We need to ignore that one. And now the second part is that because of the virtualization layer, all of the physical devices are not visible to the general virtual machines like the VM1 or VM2 here. So in order to control the actuators, we need to access to the physical device, and this physical device can be accessed through the VM0. So this is just one of the design we can use. We can also have another separate VM which have the driver running and expose the device to that VM, but we didn't use that design here. So this is the architecture when we run the racing car in the artisan environment, and we get the AutoV. Now we did the experiment trying to answer 3 questions basically. Can the safety critical applications, basically the autonomous racing applications, to run in the virtualization environment? Can the interference hurt the safety of automotive applications? And can Artisan eliminate such interference and guarantee the safety? So these are 3 simple questions we always ask in our community. So to answer these 3 questions, we set up an experiment. And this is kind of just a subset of the functionality for the car. So we want to run the car in a straight hallway for 5 seconds and let the car brake and stop at the end of the hallway. There are 2 types of the workload running. The type 1 workload is the racing car application you have already seen in the video. And the second type of the workload is the interference task. The current interference task we use is the CPU intensive task. This task will spin on the CPU whenever it gets scheduled. In the future, we also need to consider other type of the interference tasks like the cache or memory intensive tasks. There are two scenarios. One is the solo scenario, when only the racing car application runs. And second one is the interference scenario, when both the racing car application and the interference task runs. And for each of the scenario, we have 2 environments. The Linux environment, where Linux run directly on the hardware and have the application running on top of the Linux. And the second one is the virtualization environment, which we run then Artisan and under the Linux. So if we run the credit scheduler, that's basically the default Zen scheduler. And if we run the RTDS scheduler, that's the scheduler provided by the Artisan. Now we have actually 6 experiments to do. We will first have a look at the Linux environment and compare the scenarios for the solo and the interference scenarios. Okay, I will show the video for the solo scenarios when there's no interference task running, and show basically what's the expected behavior the car should have. So it should stop at the end of the hallway. And if it's quite simple from this video, but the control applications need to control the steering of the car to avoid the car from hitting the wall. If the control application is too slow, cannot handle the workload, the car will drift to the left. So now let's run the interference task and see what happens. Probably you know what will happen. Right. We limit the speed of the car because we don't want to just crash the entire car and cannot do the rest of the experiment. Okay, so this is the result. Without the real-time guarantees, the safety of the car will be violated, which is kind of known to us. Now we want to know if the racing application can run in the Artisan environment and can Artisan eliminate the interference. So let's look at the Artisan environment. Instead of showing one video, I like to show 2 videos at the same time and let you guess which one is the scenario that has the interference. Okay?
It's just a rough. Okay.
So can anyone try to guess which one is the scenario with interference?
The left one.
The left one.
The left one?
The right one.
Why?
Definitely yes.
Okay.
No, I saw it drift a little bit to the left in the beginning.
I also had the impression for the right one.
Yeah.
Actually, both of them are the same. Both of them the same because like we can if we don't keep the car running in the middle of the hallway, so that's why it drifts a little bit. Yeah. So okay, so actually it's very hard to tell the difference. So this is the result. Basically, you're right. So the right one is the interference scenario. But because the scheduler can limit the resource usage from the non-real-time VMs and can guarantee the resource supplied to the real-time VMs, we can achieve the real-time performance for the real-time VMs. So we actually also have the experiment for the Zen credit scheduler. And due to time constraints, I won't show the video here, but this is the result. So you will see the scenario similar to the Linux environment when we run the interference task in your VM, and the car will drift to the left and crash. So with this sixth experiment, we can answer the question that the safety critical application like the autonomous driving applications can run in the virtualization environment, and the artisan is a promising technique to eliminate the interference and guarantee the safety. So to conclude, we introduced the AutoV and Automotive Testbed for real-time virtualization, and we demonstrate that the automotive system integration needs the timing isolation, and the real-time virtualization is a promising technique to achieve such timing isolation. Actually, there are several challenges when we are doing this work. First one is we are asking how much evaluation should we do to claim the real-time virtualization can be used for automotive systems. As you already see, this experiment is more like a work in progress work, and it's quite preliminary. And also how to manage the other type of the resources like the network, I/O, and memory bus interference. We could probably borrow some ideas that's been introduced in the previous talks. As a future work, we like to evaluate the other mechanism of the artisan, like the dynamic cache management we proposed this year, and also we want to make it available to others so that our community can help develop more complex applications to make the scenario closer to the real scenarios. So this work actually is collaborated with a lot of people. Like the autonomous racing car collaborators, some of them are sitting in the back of the room, and you have already seen the pictures. And the Artisan project is collaborated with the Washington University. And if you like, you can check the website for the other videos. Okay, so thank you very much. This concludes the talk.
Thank you very much, Meng. And we have some time for questions.
All right. So when you did the comparison with the Linux baseline, did you use get FIFO or get deadline for the real-time tasks?
Sorry.
So you had the video, right?
Yeah.
You had was interference with Linux suppression to the wall.
Yeah.
What did you do to the real-time tasks?
I didn't do anything. I just used the.
Right. So Ross uses CFS in the background, which is totally built for systems that are very. I mean, they don't expect a high load, right? So it's sort of a straw man that you're pushing over there, right? I mean, just apply get FIFO or get deadline, and it should probably work drive straight too.
But okay, so for these scenarios, if you just use the FIFO, right, and you configure correctly, the FIFO actually will be reduced to read monotonic, and you can set the fixed priority scheduling, and you can just set the racing application to the highest priority. That could be one solution, right? That could be one solution. But when the workload becomes more complex, the Linux just using the FIFO scheduling won't be able to handle it.
Then use get deadline, which gives you reservations.
Sorry.
Use get deadline, which gives you reservations.
Yes, actually, I also think about using the Linux RT to get more reservations. but that's yeah. So I didn't have time to compare if we use the RTOS for the interference scenarios in the Linux, and that's also not the intention here. So because here the purpose is to show the possibility of virtualization in the systems, and then video is just to show like if we don't do anything, what's the worst thing may happen.
Sure, but I think it would be more compelling if you actually sort of show how a properly configured Linux crashes.
Okay. Okay, that's another future work.
All right. Any other question? Well, I do have a question. So, seems to me that you're not using the GPU here, right?
No.
You said that you couldn't have SAN and the support for the GPU working together. So that makes a lot of sense. Yeah, I know what the problem is there. However, you're still using Vision to control your, or you're using the
LiDAR. We are not using Vision.
Well, either way, you have a lot of I/O. So your system is heavily relying on timely I/O and relatively high bandwidth I/O. So now, what you showed is a way to control interference on the memory. Do you expect, or do you have any benchmark, or do you have any prediction of what happens if instead of loading the memory, one starts loading the I/O, so delaying I/O traffic with heavy, say, network traffic?
That's a good question. So right now, Zen doesn't handle the I/O. So, or to be specific, Artisan doesn't handle the I/O. So I would expect the performance will degrade, and if the degradation is allowed for the autonomous driving applications, it probably will crash, and that's why we want to evaluate the systems with other workloads. So then we want to expose what's the limitations of the current systems, so that we can also know how to improve it. Okay, what should be improved as the next step?
Makes a lot of sense. In fact, the fact that you're using Cortex A15 is K1, correct? So you have virtual extensions. To some extent, virtual extension could allow you to virtualize the I/O, but the key would be how to do correct time-oriented I/O virtualization. It's something that actually I'm personally also interested in this time. But yeah, thanks for asking. So thanks for your answer.
One last?
Yeah.
Very quickly, you have the device drivers, the application in different partitions. Did you measure or have a sense of the overhead of that communication?
No, I haven't measured that one yet, but that's a good question. So the network part right now we didn't. We have the intra-domain real-time communication framework, but it's not incorporated into the mainline of Artisan yet. So the network part we didn't measure the overhead for this application yet. So this is why right now it's just to demonstrate the possibilities, and then we need to explore more with this application and with richer capabilities for the autonomous racing car, and also more scenarios from the interference task.
Thank you.
Quick question for you, Meng, and this builds upon what Bjorn said. How should the F110 platform be changed such that Artisan would illustrate something that real-time Linux couldn't handle?
Okay, so this right now they use the NVIDIA Jetson board. Actually, this is it's not a virtualization friendly board, and I would say in order to use the cache management, and we need an Intel board, which Intel can provide in the this year, and also for the I/O, I think with the Intel board we can still handle it with the I/O virtualization. So I would say probably the Intel board is better for the Artisan if we want to handle more.
That's an interesting insight.
But the problem yes, I know the problem is for the automotive, Intel board is not a good fit. So right now it's the dilemma is the the ARM support for the NVIDIA support for the virtualization is not very good. So most of the time it's spent on the porting part, and most of the techniques used in Artisan are actually architecture independent. Once we evaluate in the Intel board, and we can also simply migrate to the ARM board when ARM has better support for the virtualization. That's my observation.
All right, very good. Well, thanks again. Let's thank again the speaker and.